开始要直播了吗？
对，不过他这边我找不到网络，所以
这边找不到网络。
对啊，所以我现在只能用我的手机。
找不到网络，有没有？昨天没有人来测试一下。
之前用都 OK 啊，对啊，昨天比较晚。
有啊，有5G 啊。
因为我是用我的桌机啊，所以现在
这里面那个网络限制。
对啊，因为我用网络限制啊，但就是他这边的网络 IP 跟我去年用的 IP 不一样。
那就只好从这边接收，然后传出去。那这个频宽够宽吗？
不知道，应该是还好，是看起来是还好。然后我问，就是这几天不知道，就是实际线都是能不能好像还没到。
现在还没到。
应该是到了，但是我打电话找不到。
Okay, I think we have already delayed for a certain time, and the technical problem will finally be solved partially. So I would like to start this year TYTD 2020's final section. Okay, starting from introducing myself. I'm Yongyuan Xu from National Taiwan Normal University. I'm the chairman of this tournament. And we have, after 2 days, very exciting competition, we finally have 3 teams for our final competition. And because of the pandemic problem, so this year we reduced the physics fight from 5 rounds to 4 rounds. And also we restrict any visitors to visiting our tournament. This is quite kind of bizarre according to our TYTD tradition. Okay, but I think despite all this kind of problem, we still have very good physics fight and a very fruitful result. And hopefully today we will still have very good physics presentation and very good physics discussion and bring us very good result. Okay, anyway, so we start from each team introducing themselves, then I will ask all the jurors to introduce themselves. So start from Miracle, please.
Hello everyone, I'm the captain of Team Miracle from CK High School. My name is Wu Zhengwen, is Ye Donghan, Liao Yuquan, and Yang Laohan. Thank you.
Okay, then please all-nighter.
Hello everybody, it's a pleasure to be here. My name is Jonathan Bruce, and I am the captain of Team All-Nighters from Taipei American School. And these are my team members, Richard, Daniel, Austin, and Gruber.
Okay, thank you. Then, Excelsior.
Hello everyone, we are Team Excelsior. I'm the captain of He Su, and there's my teammate Tai Xinzhang.
林佩宇、蔡莫恩 and Junting. Thank you. Thank you. Now I would like all the jurors to introduce themselves. Start from Professor Ye.
Good morning, everyone. I am Ye Wang Qi from National Donghua University.
I am Ping from Academia City.
Hi, my name is Min-Chuen Chang from Grand Catholic University.
And Wen Yu from Zhongli University.
施敏志从中兴大学。
Hello, everybody. I'm Xiaomang Cai from National. Okay. Okay, say it again. Xiaomang Cai from National Taiwan University. Hi, everybody.
I'm Hui Chen from National Taiwan Normal University.
Xu Hongyu from Zhongli University. I'm from Zhongyuan University. Thank you.
Okay, thanks all the members who introduced themselves. So we would like to start today's first round tournament, starting from the preparation of the reporter for 5 minutes. So please tell me whenever you are ready.
Testing.
Okay, I think the preparation time is almost up and the reporter is already ready. So please start your presentation. Your time is 12 minutes.
Good morning, everyone. I'll be presenting to you problem number 15, paper part. So the problem statement is as follows. If you take a social paper part and just shake it, contents will pour out relatively slowly. However, if the object is dropping along the bottom of the pot, the rate of pouring can increase dramatically. We are asked to explain this phenomenon and investigate how the rate depends on some parameters. This is our outline of our presentation. First, I'll show you our experimental method, which we aim to recreate the phenomenon. Then we'll do some preliminary experiments to determine the ability to conduct this experiment. Then we'll provide a theory to explain the difference in the rate of pouring, which is the structure. Last, we conduct an experiment to determine the measure of the rate of pouring and compare that of the shaking and rubbing process. Then we provide a theory to an interesting phenomenon we discovered when conducting this experiment. First, the policy definitions differ in salt. We decided to choose salt because salt particle is more even in size than mass. And what's more, the gas at the bottom of the salt particle might also improve. This about how rubbing can increase the rate of pouring. As you can see, the bottom of the particle is corrugated, which means that the edge has a wave-like structure. And so that when you rub it, it vibrates and creates a vertical acceleration, giving that as key to rate of pouring. So to recreate that said acceleration, we use this vertical shaking machine, which is connected to function generation. Function generation, which is an input in control. But first, we want to see the impact of humidity on our experiments. So first, we use a very spice that came right out of the bubble. So is pouring constantly without any resistance. But after 10 minutes, after leaving the oven, we began experiencing some difficulty pouring out salt. We decided that this is the phenomenon that the policy wanted to investigate. So for now on, for every experiment, we will microwave the salt for a certain period of time and then take it out and rest it for a certain period of time to control. What's more, we plot all the rules because I believe that one whole thing resembles the whole phenomenon and it provides a much clearer observation. To explain the cooking of coal, we believe that the salt can form a structure which is held up by static friction. By putting a camera beneath the pot and then aiming the camera upwards, the observation confirms the theory. The clear picture, you can see that it does indeed form a large structure. So the dome structure can extend a lot of pressure and pump the hole so that no salt can cross. To unplug the hole and to activate the dome structure, that's using vertical shaking machine. First, we control the temperature to roughly unit resistance. So we control the temperature to such a decided we measured that above a certain frequency, only above a certain frequency can the salt time movement is social meaning. Let's see a demonstration of social. So the focus classes have the social gravity limiting. But once if we using the soul part as a governance when you view the inside the system, so faces a fictional force and pain upwards. So when A is raised with G, it cancels out the gravity. So the current rate becomes zero. And then it can no longer sustain the motion and creating causing the proportion. In the experiment, we quickly decrease the frequency of temperature, creating an explosive acceleration. But as you can see in this plot, even if after we compile, even if the acceleration is as low as 2.19 meters per second, so it can still continue to fall. We use a scale to measure the amount of salt being poured. As you can see, when you shake water, the main difference is that throughout this whole shaking period, only 13.84% time is salt being poured. Other times it's just meaning this and shaking for but if we take out this boiling time and measure the boil rate, we can discover that the shaking, the maximum salt that goes out between shaking and rubbing is basically the same. So we can now deduct that the main fundamental difference between shaking and rubbing is not how much salt can be poured through the hole, rather it's how long the time period the salt is pouring through. We wish to explain the phenomenon which was shown before that when the salt is super dry, salt can flow through freely, but after 10 minutes, the humidity increases and then it becomes more liquid. And searching through references, we find that we decided that this phenomenon is caused by shaking, which is when water molecule goes between the salt particles and forms a hydrogen bond, which makes the salt particles stick together to form a larger particle, and thus making it much easier to talk and create the influence of polar weight. Now, to conclude our experiment. So, what is stopping the salt from pouring is forming of node that's why the frequency of breaking the node structure is very important when we want to decide whether shaking or rubbing is going forward. This can create a faster pouring rate. To start pouring, you must add a logical acceleration to it. That's internal acceleration breaks the node structure and then allows the results to start to form. Finally, by examining the humidity, the raw humidity based experiments, we decided that the existence of water is very important because when there is water, all hydrogen gas that sticks salt particles together to form a large particle, and that greatly influences the rate of pouring. And that was my presentation. Thank you.
Okay, thank you for your presentation. Next will be the question of the opponent to the reporter for 2 minutes, please.
First of all, thank you very much for that wonderful presentation. Just a couple of quick questions for you. So first, you mentioned you plugged all other holes except for the one hole where the...
Sorry, can you please remove the and then repeat the question?
Okay, so you mentioned that you plugged all other holes other than the one hole in the center. So do you think that if you increase the number of holes, the flow rate would be proportional to the number of holes?
I believe that one hole can be representative to all the phenomena that is relevant to the experiment.
Okay, and also you said that you only tested vertical vibration, but do you think that any possible horizontal vibrations might have the same impact on the flow rate?
Yes, it might have, but the rubbing creates a vertical acceleration, so that's not possible.
Okay, thank you. And also, do you think that the height of the particles in the container matters? In other words, if there is only a really, really small amount of particles in the container, do you think that the phenomenon will remain the same?
I do not believe so.
Okay, thank you. And also, do you have a way to quantitatively predict the flow rate or like any simulations?
Yes, we quantitatively measure the flow rate as roughly the same thing. Let's say certain value. We quantitatively measure.
Okay, and also, do you think that, I know you tested only salt particles, but do you think that if we were to change, for example, the hardness or the coefficient of friction or the size of the particles, that would have a significant impact on the flow rate?
I believe that's if the size of the machine concept, we will not have much other than the size.
Okay, thank you very much.
Okay, thank you. Now, time is 3 minutes time for opponent's preparation. Okay, now I think preparation time is up, so the following will be the opponent will take the floor for maximum minutes, followed by discussion between reporter and opponent. Any time remaining time during the 4 minutes will be added to the discussion time. So please start your presentation.
Okay, hello everyone. First of all, I would like to once again thank Miracle for their wonderful report. I am Jonathan Bruce and I will be opposing this topic for the all-nighters. Okay, so let's begin with the problem statement. So there it is again, and my ideal method for examining this problem statement is explaining why shaking and rubbing affect flow rate and the differences between them, which I think the reporter did rather well. Also modeling how rubbing affects the flow rate and how do different parameters associated with rubbing affect the flow rate. Okay, so I'd now just like to evaluate some pros and cons of the reporter. So the pros, he had very detailed observations of the phenomenon occurring, including some very nice photographs. He very clearly stated the comparison between shaking and rubbing, which is a key part of the problem statement. And he attempted to control a variety of variables, for example, the humidity, which is very important. He had very clear diagrams, and he considered the very interesting phenomenon of caking. However, as for cons, the graphs were sometimes unclear as to units and error bars. He also didn't, because a key part of the problem statement is how can rubbing increase the pouring rate dramatically compared to shaking, and he didn't really address this because the flow rates were quite similar that he showed in his graph. Also, there was a lack of a quantitative model to actually predict what the flow rate might be. That's dependent on different parameters. And I think that the presentation could have been just a little bit longer. So there are 4 main areas that I would like to discuss during this discussion. So the first is how does the reporter's theory account for certain particle characteristics like the coefficient of restitution, the coefficient of friction, and the Young's modulus of the particles. And also questions about their experiments and their experimental setup. Revisiting the differences between shaking and rubbing, and specifically why rubbing might have a dramatic increase as opposed to the very minimal increase that they showed in their data. And also, I would like to propose a potential quantitative theory that they could use to potentially model the phenomenon and maybe even create some computer simulations to predict what might happen under different circumstances. So with that in mind, I would like to launch into the discussion now.
Okay, please start the discussion.
Okay, so the first topic I would like to address is you used salt particles for your experiment, and humidity and the hydrogen bonding is a major factor for those particles, right?
Yes.
Okay, so let's say that you instead used other particles that were not as affected by the humidity and hydrogen bonding. Do you think that particle characteristics like the hardness of the particle, the particle's coefficient of friction, and maybe even the Young's modulus of the particle might have a significant effect on the flow rate?
For friction, yes, because as in this stated in my presentation, the road structure, the one main reason the road structure for this is friction. And I can clarify on how Young's modulus go.
Well, essentially, because one thing that you stated very clearly was the vibration caused by the rubbing. So, in my opinion, particles associated with the hardness or elasticity of the particles, like the coefficient of restitution, which basically...
So as long as the particles are not very elastic, it doesn't really have too much influence, because we view the salt as a salt particle as rigid.
Okay, do you think that the phenomena might be significantly affected if the particles were more elastic or easier or like softer?
Yes, but that will be the whole because it is so different.
Okay, yeah, I would definitely agree with you that these parameters are very important to test, and I definitely think that if you were to do further experiments, you might want to try and consider those, because those might drastically affect the flow rate, especially considering that So another thing, so can you go back to the slide where you compare the flow rates for shaking versus rubbing? Okay, so the problem statement says that the flow rate out of the pepper pot can increase dramatically with rubbing as opposed to shaking.
Yes,
So
that is a major finding. That is a major finding. Because the flow rate that side is determined by the amount of salt that pours out over the actual flowing time. So we're determining that the actual flowing time is very small proportion of the shaking time.
okay, my question is, if you could go back to that again, why do you think that the difference is so small between the two? And do you think that this could be explained, for example, by like experimental error, or do you think this is actually accurate?
It should be accurate because once the bone structure is broken, the salt can now flow through freely. As in both cases of shaking. The only difference is the frequency of the breaking of the dome. What happens after the dome breaks is that the salt can flow through freely. Then that's basically the same. So that's the question.
Also, I'd just like to clarify something. Do you have a quantitative distinction between rubbing and shaking? Because both of them are types of applied oscillations to the system, but do you have like a specific amplitude of oscillation where you consider it a transfer from like rubbing to shaking or something like that, or a specific frequency?
So shaking, we use shaking. The motion you use shaking should be fundamentally different.
Okay.
Different than shaking. We use shaking by hand, but then we use rock when rock is. We also use hand to rock salt hot, and then we use trackers to determine the frequency, which is what then we reproduce using the oscillator.
Okay, so just to clarify, did you obtain that graph of shaking versus rubbing when you were shaking it by hand and rubbing it by hand? The graph on the next slide, go back to that graph. Yeah. Did you attain that graph when you were doing the experiments by hand?
Yes.
Okay, well, don't you think that would introduce a significant amount of error because you can't exactly control the rate at which you can shake it by hand relatively accurately?
I think in a theory it is quite clear that but if you only want to examine the flow rate, the movement of the salt flowing freely, it shouldn't be measured too much about the method in which you shake the bottle. Because when you're shaking, and any kind of shaking should do the same thing, which is break the structure and allow the salt to flow freely.
Yes, I agree that shaking will break the dome structure regardless, but I still think that the amplitude and frequency of the shaking do have an impact on the pouring rate, and that if you want to get really accurate data, you might want to consider not doing this by hand and having some sort of a mechanized setup to control the shaking parameters. And also so using like a motorized mechanical setup. Okay. Just to clarify, because I didn't get this quite clearly during the 2-minute questioning, so do you have a quantitative theory model that can predict the flow rate under certain circumstances?
Circumstances being, what parameters are you thinking about?
I mean, like just basically the parameters that you tested. I mean, do you have a theory model that can quantitatively predict the flow rate for different parameters?
The model should be fairly easy because of the critical yes. So it should be quite easy because above this certain acceleration, the core rate should be close should be as the last graph showed is 27. Beneath this it should be zero. It's basically all.
Okay, but just to be clear, is this your experimental data or is this a theory prediction? What I'm asking is if you have like a computer simulation, for example.
This is a data generated by function generation.
So as for a theoretical model that might be able to predict this, might I propose an equation that could help with this if we want to predict a computer simulation? So this equation is called the Beverly equation. It's commonly used for modeling the flow of particles through an aperture. So essentially the Beverly equation is generally written as follows. Correct me if I'm wrong, I might not remember this exactly. But W is the mass flow rate, and this is related to a certain fitting constant.
Should we focus on my
Oh no, I'm just suggesting this is
relevant to the experiment?
well, I'm suggesting this is a potential modification to your theory so that you might be able to quantitatively predict what happens here. So anyway, if I may finish writing out the equation, yeah, you could potentially use this to help.
So you get this from such a reference before in your own experiment?
Well, I just think that this equation in general is very applicable to this phenomenon, so I do think that you might want to consider using this because this models how the flow rate changes with different particles, like the diameter of the particle, the characteristics of the particle. So you might want to consider using this in your theory if you want to quantitatively predict what might happen. Just a suggestion. Okay.
Yes, I might want to check into the applicability into my experiment because that is clearly something your own experiment.
Well, this is just a general model. This isn't necessarily specific to my own experiments, but anyway, actually, speaking of the parameters that are addressed in the Beverly model, I would like to ask, did you consider the size of the hole as a relevant parameter in this experiment? Because, correct me if I'm wrong, I didn't really notice the graph that you had for that, the actual size of the hole, which the solvent is flying.
No, but the size of the so-called parameter to hold to it remains constant in our experiment. So okay. Change it.
But don't you think that that might be a relevant parameter that you can test? Don't you think that changing the size of the hole might change the flow rate and potentially even the phenomenon of jamming?
That might be correct, but that might, if you increase the hole too much, I think you will realize the phenomenon can no longer be observed.
I definitely agree with that, but I also think that within a certain range of hole sizes when the phenomenon is observed, you might want to consider testing the hole size as an additional parameter in your experiments. And also, might I add the particle sizes as well, the particle size. I know you used salt because it was a consistent particle size, but maybe changing the particle size within a certain range might be able to provide you with better insight into the phenomenon.
I think you might have before.
Yeah. Okay. So I think that pretty much answers all my questions. Thank you very much.
My pleasure.
Okay, so after the discussion, please spend, you have 1 minute to summarize the discussion, please.
Okay, so I feel that we had a very fruitful discussion. So I proposed several additional parameters that the reporter might consider when examining this phenomenon, such as the size of the hole, the size of the particles, and the characteristics of the particles, such as related to friction and their elasticity. I also proposed a potential mathematical model that the reporter could use in theoretical simulations, and recommended that the reporter consider using a more mechanized setup to better control the amplitude and frequency of the oscillation rather than doing the experiment by hand, which might be relatively inaccurate. So, thank you very much.
Okay, so now we proceed to the question of the reviewer to the reporter and the opponent. Please, reporter and opponent, stand on the stage. Okay, please start.
Okay, so it's for the reporter and the opponent. I would like to ask if discuss about the rates of rubbing and shaking. I would like to ask both of you if the direction of the oscillation of the part is affecting the rates to increase or the decrease density between particles affecting it.
So just to clarify, by the direction of oscillation, do you mean like vertical versus horizontal oscillation?
Yes.
So let me answer that. In my experiments, we use vertical oscillation to better reproduce the.
I think it's the direction of oscillation is affecting it.
That is also a very variable we consider.
You didn't consider it in your experiment?
No.
The direction of the oscillation.
So
do you think
if you change the direction, you might have some.
Do you think it's the direction of oscillation is affecting it?
You might have some.
And for the reporter, do you think which one is it?
Well, I think that the direction of oscillation might have some impact, but ultimately I feel that both vertical and horizontal oscillations will break the dome structure and will cause the particles to flow more easily through the hole. So I think that both should have a similar effect, if not exactly the same.
They do have a similar effect to it. You think they do have this similar effect to it?
Oh, well, I'm stating that I believe that vertical and horizontal oscillation should have a relatively similar effect on the flow rate.
Okay, thank you. So for both of you, so shaking is a vertical vibration, right?
Yes.
And rubbing is a horizontal vibration to the pot.
Incorrect.
Yeah, I agree with the reporter on that. Because of the grooves on the bottom of the pot, rubbing does produce
Okay,
vertical
so
oscillations.
I wanted to ask if there's a vertical vibration and a horizontal vibration. If you control the frequency and amplitude of it, control both of it, and what the vibrating pore rates will be the same in these two different directions, and you control the frequency and amplitude of it.
You mean the rubbing is vertical direction only. We simulated with vertical direction only.
So you assume that while you're rubbing the pot, there's only vertical vibration in the pot?
I think that is the only direction that is
relevant.
relevant.
And you agree?
I would mostly agree with the reporter. I think depending on the experimental setup, rubbing might produce some horizontal vibrations, but the main vibrations I feel are vertical.
Okay, thank you.
Okay, now we proceed on to the preparation of the reviewer for 2 minutes. Okay. I think now is the time for the reviewer to take the floor for 4 minutes. Please start.
So this is a reviewer from Team Celsius and the problem statement we're going to talk about is pepper pot. So this is the problem statement, and if applied is dropping on the bottom of the pause, then the rate of quarter increase dramatically in investigative phenomena and the level of parameters that affect the phenomena. And this is the reporters online. So first of all, I think there will be, so there's lack of theoretical equations in their report, and they only consider one hole in their experiment, but as in my opinion, they should consider more, like the number of the particles should be considered in it. And there's no theory supporting the phenomenon, like they only mentioned that caking and the null structure, but there is no equations to qualitatively explain the phenomenon. And there is lack of parameters that, like size of particles and holes, they can be considered in it as parameters too, but they didn't. And for the pros of the reporter, the variables like humidity and amplitude were well controlled in their experiment, and the movement of particles are analyzed. And this is the opponent's pros and cons. First of all, our opponent mentioned the differences between shaking and the Barlow equation and other particles characteristics in the Young's models. And the pros of the opponent is that he mentions the quantification of experiments and other parameters considered and discussed. And there's innovative theory equations suggested. And by the reporter, by the opponent has lack of questions. They only have few questions to report it, and there's too much time comparisons instead of the analysis. And there's he did not mention his own opinion in the discussion. And for the discussion, the opponent asked about the differences of the shaking by hands, and what replied the vertical motion is only in shaking motion, and the experiment setup is still accurate according to the result. In my opinion, they should consider both frequency and amplitude in the experiment, and also I agree with the opponent that the poor setup might cause the horizontal motion. And this is a discussion about size of hole. The opponent asked if to consider about it, and the report says the size is too large, the phone might be affected. And the report thinks that I agree with the reporter that if the hole is too large, the phone might be affected. And this is the discussion of friction and excited particles, and this is the discussion of plate 2, and I think that I'm convinced by the reporter that the size of particles was too large to assume. And these are the pros missed. First of all, the motion of rubbing and shaking, and the theory, the recovery are not considered in both of them in the discussion, and the collision between particles are not discussed also. And pressure, while the reporting the time, the mass of the particles will affect the pressure, and during the time the pressure will be different. So I think we should consider. Thank you.
Okay, thank you. Now we proceed to the concluding remarks of the reporter for 2 minutes. So please start.
And also, again clarify to my opponent that I already explained that the pouring rate, the problem stated the dramatic increase in pouring rate is caused by the actual time period in which the salt can pour. So, and the point is that the reviewer just mentioned that the mass can create a pressure on our weight, but we waited until the mass is stable so that the pressure is only caused by gravity. Next, the reviewer believes that I did not provide a clear theory, but I actually developed a very successful theory regarding apparent force, apparent weight and frictional force, and it matches with our theory very well because only when A is greater, only when A is slightly greater than gravity can the salt begin to flow. I'd like to suggest my opponent and the consider the ability of some of the parameters they suggested. For example, the elasticity should not be relevant in this experiment that considers salt and pepper. Also, if you change some of the parameters, it might very well not be able to replicate this phenomenon. Also, I believe that the opponent should focus more on my experiment, proposing theory that cannot be verified if it can be applied to my experiment. And that is all for my concluding remarks. Thank you.
Okay, thank you for your concluding remarks. So I would like to invite another two teams presenters to stand on the stage and be ready to answer the question from the jurors. So any question from the jurors, please.
A question for the reporter. Are you suggesting all restaurants provide us the waste salt? Or there is another factor that is more important than hydrogen bomb? Are you suggesting that all restaurants are providing us a waste salt? Or
waste salt?
Because you say the weighting, the humidity, the caking is effective for the salt not coming out continuously. So that means all the restaurants providing the salt is wet. Are you saying this? Or there are some other factor which is more important than hydrogen bomb?
Hydrogen bomb creates caking, which then makes it much easier to form a dome structure, which then prevents the flowing of the salt.
Then all the restaurants are providing us the waste salt. You are saying this?
So for the experiments, we use salts that have been out in the air for 10 minutes.
Or maybe the opponent can answer this question.
Can you please repeat the question again?
Your argument means there has to be a hydrogen bomb which is from water molecule. So that means all the salt providing from the restaurant are wet.
Yes, I believe that most of them are wet because they cannot flow so easily when you shake it. I also know the disaster. Because if salt can be poured, also can be poured freely. I think there ought to be some hydrogen bound in the salt provided by the restaurant because you shake it and then it comes out only small individual part. Then it forms a dome structure.
Yeah, yes, okay.
Also, it's the mass of the salt being poured out over the actual pouring time, which is a time when the salt can form a constant stream.
So I think his definition is that how much time the salt can go through the hole.
It's the massive amount of salt being poured out over the amount of the time period when salt can.
Why isn't it the amount of salt affected in a certain time?
So
is it the same? Is it the same with yours? Because I'm not quite sure I understand the opponents and reviewer expressed your opinion about the pouring rate definition.
I think that the reporter actually has a good definition for this. The mass of the salt that comes out during the actual time flowing out of pepper pot.
Excuse me.
amount of time the saucer can form a constant stream of flow. Can flow through constantly. Actually, what you can mix the amount of time when the saucer is going to.
In my opinion, during the pouring time, because the particles are pouring out constantly, so the pressure on in the pot is decreasing. So in the end of the vibrating, the part rate should be smaller.
So, please.
Since we have put down the referral law, let me ask the opponent first. In this experiment, in your expression, there is no frequency. So there's no shifting frequency, no amplitude. So how does that matter to the experiment?
Well, in this case, I believe that because there is a constant K in there that basically models how hard it is for the particles to flow through the hole. So I think that changing the frequency and amplitude will change that constant K, and that's how that model can be used to model the flow of particles.
Okay, how about the portion?
I believe that the more important parameter in this experiment is the vibrating amplitude and friction. So that's why I believe this is not very applicable to my experiment.
So you think it is irrelevant?
It is mostly irrelevant to whether it's okay for.
How would the review?
In my opinion, the constant K will affected by those parameters, but using this to calculate the whole phenomenon would not be this equation cannot fully express the whole phenomenon of it.
Okay, so we will proceed to the scoring session. So I would like to ask all three teams to please the presenter to stand on the stage. Okay. To have a better look on the grades. So please, juror, to raise your card so we can read the score. So I will start from this side. So for the score for the reporter are 6, 6, 7, 6, 8, 8, 4, 8, 8, 6, 6. Then for the opponent 6, 7, 8, 9, 8, 8, 8, 9, 8, 7.
Thank you.
So score for the reviewer. 7, 6, 7, 8, 8, 7, 6, 8, 8, 6, 6. And as we would like to invite some extremely high score to give some comment. First from 4 for the reporter.
So that's me. I give a really low score because I look at the question is about how this parameter influences the flowing rate. But I think the most key result in the reporter is actually getting this critical acceleration, like 10.7 meter per second squared. So I think this is the condition for its the soul will fall or not. So it's not a falling rate. It's like a critical parameter which the soul can fall or not. So for that point, I think it didn't really quite fulfill this question. So that's why I give a slightly low score.
Okay, thank you. And then we have several 8, so anyone can give some comments. 8 for the reporter. Yeah, please.
The reporter did a very good job. Essentially, what you can do, high school level,
Okay, so for the opponent, we got 1, 6, 7, 7, 8, and 2, 9. So I think we start from the 6 the opponent. Can you give some comment?
Because you are an opponent, I think you should carefully look at the result of the report. Because the definition of a polling time will be very strict. Because that's the definition. And you will have set similar polling rate of the both conditions in the next page, page 1. Okay, so I think for the reporter job, opponent job, we should carefully look at the result of the result.
And also likely we got 2, 9. 9 for the opponent, so any comments can be given. Yeah, please. Okay, thank you. And for the reviewer, we got a pretty even distribution, 4, 6, 3, 7, and 8. So I think there's no obligation to give comment, but we are welcome to give anyone who would like to give comments. Okay, no. Thank you all, and thanks to the teams and for judges. We will have 10 minutes break. Then we will have the next section. Okay, thank you.
对，我打完分数之后，他说要叫起来的时候，我才看一看我旁边的，结果刚好是他们两个。
Hello.
他在吗？他今天应该会在啦，今天不来啦，因为我不知道是他写的。
他来应该是
他回去了吗？
没有，接下来他的事。他是大的。 对啊。
Okay, I think all the technical problems are all solved. Now we would like to start the second round of the final physics fight. For this round, the reporter will be all-nighter. The opponent will be Excelsior, and the reviewer will be Miracle. And the problem to be presented will be seeing Ferrite. So we start from the preparation of the reporter. Sorry, the clock is wrong. Okay, we started the preparation time for the reporter for 5 minutes. So inform me whenever you are ready. Okay, since the reporter already finished their preparation, so we will start the reporter's report for 12 minutes. So please.
Good morning. I'm also from Team All-Nighters. Today we're presenting problem number 4, Team Carol. So the problem statement is, insert a current rod into a coil fed from a signal generator. And at the rod begins to produce sound. And we're actually in the phenomenon. So our research has 3 main focuses. First, why does the ferrite rod produce a sound? Second, what are the characteristics of the sound produced? And third, what are the relevant parameters that affect the frequency? Okay, so this is a brief outline. We're going to start with phenomenon investigation, then the theoretical model. After that, the experimentation and discussion of results. Finally, a conclusion. So starting with conceptual description. To understand why the ferrite rod makes a sound, we first know that it is restricted. This means that the material changes in volume, either expands or contracts when subjected to a change in magnetic field. So as you can see, when the field is applied, the domains rearrange. And this rearrangement causes the shape to change. Okay, so how is sound produced? The wave generator delivers an AC current to the coil. In this coil, an oscillating magnetic field is therefore created. Because the field's direction is constantly changing, the rod will continuously expand then contract. This vibrating motion causes the sound to vibrate. Now, if this vibration matches the natural frequency of the rod, then resonance causes a sound to be produced. Okay, so let's investigate how rod vibrates. So here we can see the domains rearranged in a circular motion. This causes the rod to both expand vertically and also horizontally. We can model this vibration using a longitudinal wave. Also, because the domains rotate, they would induce a transverse wave on the rod. So, a transverse wave is created. So, starting with the theory, for the longitudinal wave, we have a force diagram. So in here, the piece is x, and dx represents the thickness of the piece. Now, when the field is applied, the rod expands, so a left force exists and a right force exists. Now, the force is larger in this case, so the rod would experience a net shift to the right. We model this as u, the displacement of the piece. But not only does it move, it also expands. So we model this stretch as du. Now, to model this motion, we use equation. Stress equals the Young's modulus times strain. In this case, stress is the pressure, so it's the upper area, times the Young's modulus, and the strain is the du stretch over the thickness, dx. Then we apply Newton's second law to the force diagram. F equals ma. In this case, a is the double derivative of the stretch, u. Therefore, on the left, we combine the right and left forces. Right, rho density times area times dx is the mass. And we have the derivative of the time. Okay, so our ultimate goal is to find the frequency of the rod. So we can model it using a wave equation. In this case, c represents the wave speed. When we combine our previous equations 1 and 2, we can make them into similar form, and we get that the wave speed equals the square root of the Young's modulus over the density. Okay, so before we move on, let's set the boundary conditions. In the coil, the rod is middle. So in the middle, the left and right forces are equal. That means the stretch equals 0. The boundary condition is on the two sides, there's no more force, so du over dx is 0. Okay, next. Now we try to model the rod's resonance as a standing wave. We'll use the standing wave equation, u as a function of position and time. When we solve the equation and plug in the boundary conditions, we get that the resonant frequency of the rod is equal to the harmonics minus 1/2 over the length of the rod, the square root of Young's modulus over density. This is important because it tells us the relevant parameters that affect its frequency. Okay, now moving to the shear waves. The main difference between shear wave and longitudinal wave is longitudinal models the stretch using Young's modulus, how much it can stretch. But for the shear wave and models using the shear modulus, how much the rod can bend vertical. So we simply substitute G for Y in the wave speed. Okay, so the rod is held by two strings and a coil, and then it creates three boundary conditions. First, the middle is fixed, the two ends are open. Second, one is fixed, and third, both ends are fixed. And we solve for the frequency equations, as shown here. So the experiments and results. This is our experimental setup, and you can see a wave generator is connected to an amplifier. The amplifier is meant to amplify the current, so we have a large enough magnetic force to drive the rod. And the rod is hung in the middle of the coil. Now, to quickly find its resonant frequencies, we perform a function called the frequency sweep, where we sweep from 100 Hz to 30 kHz every 2 seconds. This is helpful because when the sweep matches the resonant frequency of the rod will ring. And since the rod has harmonics, every cycle of the rod will ring several times. So this allows us to quickly find its resonant frequencies. Okay, so this is how we report out. We first measure the background noise to reduce error. Then we record the readings for 3 minutes. Since each cycle is 2 seconds, we record a total of 90 cycles, and this rules out any disturbance during one cycle. We then use an FFT to find the resonant frequency of the rod. Okay, so this is our experimental overview. The independent variables are the length of the rod, its Young's modulus and shear modulus. For experiments, we split it into 2 sections. First, the longitudinal wave, and second, the shear wave. For longitudinal, we find how the length of the rod affects its frequency. For shear wave, we find how the shear modulus, or the material of the rod, affects its frequency. So, this is an example of an FFT. Here we see 4 resonant peaks, but we don't know which one is shear, which one is longitudinal. So we do that by attaching tape to the rod. This dampens the rod's vertical vibration, allowing it to only expand horizontally. And in B, we find that only one frequency, the longitudinal frequency, is created. Okay, so for our theory, we have frequency, length, and density, but we can't theoretically find its Young modulus. So we use it, we find it experimentally. Here we plug in the known length rho and F, and we saw that Young's modulus is about 150 gigapascals. So the rod is very stiff. So this is the first experiment on longitudinal waves. Here we can see that length and frequency are inversely related. The red is our experimental data, and the blue is our theory curve. You can see they match very well. Okay, next one. And we also perform an experiment on shear waves. This table uses 2 rods of the same length, but different material. Using the same way we find the Young's modulus, we find that they indeed have different shear modulus. One is at 50 GPa, the other is at 60 GPa. Then we find that for these rods, they normally have a multiple of 2, as shown by the 2 rows, first 2 rows. And comparing the first one and the third row, we have a multiple of 3. This proves that the rod has multiple boundary conditions. First, one end is fixed, and this harmonics is exactly times 2. And the second is the middle is fixed. And then when we plug in the shear modulus into our theory equation, we get that the blue values, the theory values, match our experiments pretty well. 9 and 10, 13 and about 12, 15, 15, and 19, 19. So now let's analyze why there's a deviation. The cause of error may be Doppler effect, because when the rod is oscillating, it's moving back and forth in the coil. When the rod moves towards the microphone, the frequency will seem higher, but when it moves away, the frequency might be lower. Another cause is damping, because in our experiment we use tape or string to tie the rod. This may create a damping ratio and decrease the wave speed on the rod, therefore lower the rod's frequency. And this evidence of damping can be shown in our FFT. In the bottom, we see that the spectrum spreads out, which shows that this may be because of damping. However, we think this is less of a problem because the rod, its amplitude is pretty low. So therefore, damping will not damp the rod by a lot, or affect it so much. So our summary of our research. First, we developed a conceptual understanding of why a sound is produced. It is a combination of magnetic restriction, the domain movements, and resonance. For our theory, we found that the rod has both a longitudinal and shear wave, and we use a standing wave model to find its resonant frequency equations. Experiments, we performed a sweep method, and on the longitudinal section, we found how length affects its frequency. On the shear section, how shear modules affects its frequency. For future work, we can add in our theory to more likely predict the frequency due to Doppler effect. And also, we might improve our experimental setup to reduce damping, further increasing our accuracy. Okay, thank you.
Okay, thank you. Now we proceed to the question of the opponent to the reporter for 2 minutes. So please start.
For the reporter, your page 5. Your page 5, please. And is the real domain of the Vera rod, or is just a simulation?
This models how the domain moves in the actual flow.
I mean that is the arrangement of the domain is real of the Vera rod.
Yes.
Okay. And your page 6. Will the volume of the rod change during the magneto-restricted effect?
The
volume.
The volume.
Yeah, of the rod.
Yes, I will change both horizontally and vertically.
I mean the whole volume.
Yes.
And in your page 22, and the chart means that if you insert the same frequency from the signal generator, there have many sounds in the same frequency of the signal generator. Do you agree?
Can you repeat your question?
Then the rod will produce many frequencies of sound in the same frequency of signal generator.
Yes, because the rod has both shear waves and longitudinal waves.
In your experiment, do you consider the temperature of the Vera rod?
We did not.
You didn't. And okay. So, and in your experiment, did you choose the form of wave from the signal generator?
The
form of wave, such as the triangle or the fishbowl.
We mainly use a sine wave.
Okay. And in your experiment, did you consider the fringing effect of a coil? I mean that the magnetic field line might be separate. So the magnetic induction is not as big as the center. Did you consider that?
We try to use a ruler to place the rod in the center of the coil.
Okay, thank you.
Okay, now it's a time for opponent to prepare your presentation for 3 minutes. Okay, so I think it's time for opponent to take the floor for maximum minutes. So please start.
Okay. Honorable juries and well-members, I'm the opponent from Chicken Closer. Today I'm going to oppose the problem of and this is the proven statement. Insert the ferro rod into a coil vent from a signal generator. At some frequencies, the rod begins to produce a sound. Investigate the phenomenon. And from this proven statement, the opponent thinks that we should main focus at which frequencies that the rod will produce a sound of the signal generator. And we should mention about the different properties of the mechanism, such as the proven statement asks us to use the ferro rod to insert in the coil vent. So we should find out the pros or the properties of the ferro rod. And we should find out the sound intensities depends on your parameters. And this is the structure of sound problem. First of all, we should analyze the sound produced by the ferrite. Such as the reporter mentioned, it is caused by the magneto-stricted effect. And I want to believe that there has two times frequency from the signal generator. And next, we should investigate the sound intensity under different parameters, as the magnetic induction of the coil vent, and as the reporter mentioned, the length of the ferro rod as well as the wave frequencies. And at last, we should find out the boundary or the range of the sound to be produced. And this is the strong and weak points that I think the reporter should. And the strong point is that he has the various parameters such as the Young's modulus. And the experiment did have discussed physics theory, and he discussed the limits and property detail. And the key points are that he has a lack of very thick equations and too much time spent on the explanation of the mathematical standards. And he didn't mention the way to measure the experiments such as the Young's modulus. And he didn't consider enough variables such as the temperature or the magnitude of the currency. And he has a lack of very assumption or the limits. And this is the point that the opponent thinks should be discussed. First of all, we should discuss the definition of some frequencies from the public statement. And in the phenomenon analysis, first of all, the opponent believes that the sound is produced because of the magneto-stricted effect of the ferro rod. And the opponent believes that the sound will be significant because the resonance. So we should find out the relations between the driving frequency and the natural frequency of the ferro rod. And from the hysteresis, the opponent believes that the temperature will be caused by the hysteresis loss. So the reporter didn't mention the temperature, and they didn't control it, and they didn't change it as the parameters. And this is the first assumptions. First of all, we should find out if any forms of wave will also cause the magneto-stricted effect or the phenomenon of the frequency. And the property of ferrite that the problem statement I mentioned is to use the ferro rod to insert the coil vent. So what is the differences between other ferromagnetisms? And from the theory temperature, as we know that if the temperature is too high, then the probability of the ferro rod will have a significant effect. And from the measurement, I think the reporter didn't mention how does they measure such a huge amount of the Young's modulus. And they didn't consider the temperature also. And from the parameters, I think they should consider the temperature as well as the magnitude of the currency and the ratio of windings. Thank you.
Now, sit down to the discussion. So please start.
First of all, I would like to ask about what is the definition of sound frequency from the problem statement.
I think it is talking about if the signal generator produces some frequencies, then that will cause the rod to make a sound.
Okay, so in your chart you can see that what is the phenomenon of some frequencies of producing the sound? The phenomenon.
It is mainly because the signal generator's frequency matches the resonant frequency of the rod. So only at some frequencies the rod can make to make a sound.
So, and can you explain more about the reason that the magnetic restriction causes the sound?
The rearrangement of the domains changes the shape of the rod.
And the domain of the drift here. And as we know that the ferromagnetic domain will be arranged by a big domain and a small domain, such like this. And so from this is the anti-ferromagnetism instead of the ferromagnetism. Well, it still it has a difference between the anti-magnetism and the ferromagnetism.
Can you clarify anti-magnetism?
I mean that this is the domain arranged by the ferromagnetism. And in this drift, it is about the anti-ferromagnetism. Is there a difference?
I think the change in the field will overall cause these to rotate in the same direction. Because the dominating field only has one direction. So if the field is north and this is south, then all the domains will tend to rotate in the same direction.
They have the same phenomenon?
Yes.
Okay, I agree. And did you consider the driving force such as the currency of the coil fence, driving force frequency, or the driving force amplitude?
We, for that, use the frequency of the signal generator.
So, and did you control the wave, amplitude of the wave?
We chose not to focus on that because the problem statement states that at some frequencies the rod produces a sound.
So you didn't consider the sound intensity affected by some other parameters?
We did not do an experiment on that.
So you didn't consider the sound intensity. And I think that the sound intensity is very important because since that their charts, they have a significant magnitude of the sound. So we should find out that whether the other parameters will affect the amplitude of the sound.
Okay, so I think we could focus more on my research, and to answer your question, I think the sound intensity would increase as the current is greater because the greater current will create greater magnetic field, and that will cause more domains in the rod to rotate. So rod will have a bigger amplitude. When it has a bigger amplitude, then it will have a larger sound.
So you didn't think that the other parameters such as the magnitude, currency, as well as the ratio of points will affect that?
For our experiment,
you didn't think that. And as you said that, you didn't mention the temperature of the wet rod. And as you know from the free temperature, the magnetization will have a negative proportional to the temperature of the wet rod, such that this is the magnetization will be proportional to the temperature of the wet rod, and this is the magnetic field. So as the temperature increased by the of the hysteresis curve, this is the hysteresis curve, and this will represent the temperature or the hysteresis loss as caused during the periodical magnetic field. So in this situation, it will cause temperature, and it will also affect the magnetization. So I think it will affect the amplitude. So the sound intensity will be affected.
Okay, however, I don't, for our experiment, at least for ours, after we tested the rod, after the rod finishes vibrating, we tested the temperature of the rod and it barely changed. So I don't think the vibration of the rod will change its temperature.
So did you avoid the temperature? Did you avoid the temperature factors in your experiment?
We definitely recognize that maybe temperature changes by a little, but at a negligible effect.
Okay, I think that the temperature change will be important in the experiment. And the next question is that did you consider the fringent effect? Can you turn to the page that you have the photo effect?
Page?
Have the photo effect. You have the figure of the photo effect.
Coil effect.
Coil, like this.
The rod.
As we know that if the coil bed is finite, it's infinite long, then the magnetic induction will be the same in each point. But actually, the coil bed is a finite amount. So the magnetic field here, the magnetic field here will be less than the center of the coil bed.
But you try to place the rod inside the coil and prevent it from going outside the coil. And since the coil is solenoid, inside the field is mostly the same.
But the magnetization of the coil of the ferro rod will be equal if the magnitude of the field is not equal in the coil bed.
Yes, but we try to keep the rod in the center inside the coil.
So you didn't show
in this.
So you think that the ferro rod, but actually here's magnetic field induction will be less than the center of the coil bed. So I think that the fringing effect should be discussed, and you should mention it your. Do you avoid the spin effect of the? Do you avoid the spin effect of the coil bed as the frequency increase, then the electron flow will be centralized at the surroundings of the electron field, so the resistance will decrease, and actually it will be very hot, and probably the coil bed will be burnt or burnt out. Yeah. Did you consider it, or how did you avoid it?
Do you mean avoid the heating of the wires?
Of the coil bed, of the electron field.
I think for the machine, they mainly have resistors in the wave generator, so that prevents the current from reaching too high. Because in the wave generator, to prevent the temperature from going too high, they actually have fuses. So that prevents the temperature from going to the extent of burning the plastic coatings of the coil.
Did you didn't change the form of the wave in your experiment? So what do you think if the wave is triangle wave, such as, or the digital wave? And the triangle wave will be like this, so it is like this. And the digital wave or the square wave will be like this. Even the T wave will be like this. Did you change the form of wave, and does it will affect the magnetostricted effect in your experiment?
I think that the wave you're talking about is saying how the magnetic field changes with time. So if it's a square wave, then the field changes more discretely, changes instantly. If it's a triangle wave, it changes more quickly.
Yeah. So
but I think
will it affect the magnetostricted effect?
If you keep the frequency of the wave constant, then I think as long as the frequency resonates with the rod, then the sound can be heard.
And what type of frequencies did you mention? And what is the relation between the output frequencies and the signal generator frequencies?
I think they are.
What is the relation? Did they have did the output frequencies have the difference between the signal generator's frequencies?
I think they're pretty close. They should be pretty close.
It should be very close. Yeah. But actually, in the magnetostricted effect, as the amplitude of the alternative currency's amplitude goes back here, then the magnetization will be increased. So the ferro rod will be long. But in here, the ferro rod will be like a little bit big, like this.
Okay, I think the time is up. Sorry, time is up. So you want to answer any question?
I would like to clarify that in the coil, the magnetic field.
There's no time for you to clarify. Just if there's any question you ask, you can answer. But since there's no, you just want to clarify that answer, so no. So now is the time for the opponent to make a conclusion summary for the discussion for 1 minute.
We have mentioned the magnetostricted effect caused by the periodical magnetic field of the coil bed, and the opponent believes that there will have to
has mentioned the resonance that will cause the strike frequency to be same as the net frequency. And from the hysteresis, the opponent believes that the temperature will affect the result of the experiment. So I think that their experiment is not accurate at all. And from the theories, we discussed the different forms of waves, and I agree with the reporter that it will have also the magnetic effect. And from parameters, I believe that the temperature should be discussed instead of just neglected. Thank you.
Okay, thank you. So now is the time for the reviewer to ask questions. I would like two presenters to stand on the stage.
Okay, so to the reporter, do you have any video of your sound? Because the reviewer doesn't know the magnitude of the sound.
We do have evidence of the FFT of the sound.
No, I mean, do you have a clear audio file on your presentation so that we everyone can know what it actually sounds like?
On this presentation, no.
Okay, and do you think that the magnitude that this ferrite rod actually produces is significant enough that it isn't disturbed by other relative background noises? For example, perhaps the sound from the coil.
We did consider maybe the coil would have a sound. That's why we measured the background noise using an FFT.
Okay, but you measured the background noise, but you failed to consider that after the ferrite rod is inserted, the magnetic field isn't the same as the original one, so the background noise wouldn't be the same as well.
I think the coil's magnetic field is still the same.
So you said that the temperature changes to be negative, right?
Yes.
But have you ever thought about the scale of this experiment? The ferrite rod is relatively small, and so even a little bit of temperature change could have a very big influence on this experiment results.
But after the ferrite rod vibrated, we checked if the rod heated up, and it turns out that it is still cool. So,
are you sure that because the measurements might not be precise enough, are you sure that there isn't any little changes of the temperature?
I think still little changes in the temperature, but on the x-axis,
is there a threshold of how fast the AC frequency can be? Because if it's too rapidly changing, can it still produce any sound?
I think the frequency, for example, that's 20 kilohertz, is moving at a very fast rate. So that itself is.
So do you think that when the frequency is too high, the ferrite rod wouldn't have enough time to react to the magnetic field change?
I think as shown by our experiments, the maximum frequency is 17 kilohertz.
Okay, thank you. To the opponent, why do you think that the Curie temperature is important? Because it should be relatively high. Because as we know that the Curie temperature will affect the magnetization as well as it will affect the permeability of the ferrite rod. Because the temperature is over the Curie temperature, the permeability will have a significant effect. So that will affect the magnetization as well. Okay, thank you. Could the reporter turn his presentation to page 18? And so can you tell us how the ferrite rod was set? Because if you use the string or use tape, then the friction will also affect how the ferrite rod changes, and that will also affect how the sound will be produced.
Yes, I agree with you. The string may have dampened the rod's vibration, and therefore lower its frequency by a little bit.
Okay, thank you. The time is up. So, reviewer, you have 2 minutes to prepare your presentation. Okay, seeing the preparation time is up. So, reviewer, you got 4 minutes to make your presentation, please.
Okay, this is a reviewer from Team Miracle, and now I'm going to sum up the discussion. First, I wanted to tell what our main focus on this experiment is. We believe that they should find out the relationship between the input frequency and the output frequency, and what is the reason of the formation of the sound. And okay, as for the reporter, in his phenomenon, he talked about the change in volume and the resonance, and he also talked about 3 different waves in his theory. And in his experiment, he considered the damping of the modulus. So he gave a very clear illustration about his experiment setup, and however, he fails to demonstrate the phenomenon. And he lacks other more essential parameters such as the voltage or the current of the inputs. And also, he lacks an intuitive explanation, meaning that he gave complex mathematical models that aren't really useful for understanding this problem. And he only gave qualitative explanations, not giving exact theory of what the relationship between the frequency and the actual current is. So, as for the opponent, in his presentation, he talked about the structure of solving the problem and also the pros and cons. The pros that the opponent had is that he brought up the boundaries of the sound, the structure of the discussion. However, he wasn't talking clearly enough, and he fails to consider how high the Curie temperature is. Okay, so in his first discussion, they talked about frequency, and so the report believes that the resonance frequency matches up. The report believes that they should elaborate on other factors such as harmonics of the ferrite rod and the relationship between the input and output frequency. And for the driving forces, the report said that the driving forces was from the function generator. The report believes that they should give the boundaries that the ferrite sound to be significant enough that we can analyze them, perhaps considering how large the voltage or the current has to be. And as for the Curie temperature, the reviewer believes that it would have reached the Curie point, but the temperature should still have a very significant impact on the stabilization of the magnetic moment, since as the temperature gets higher, it might be disturbed. And okay, for the coil magnetic field, the report says that the ferrite rod was in the coil, and the reviewer believes that the coil magnetic field should still be measured, and also should have considered the field after the ferrite rod was actually put into the coil. As for the heating, the report said that there is a fuse to deal with this problem, but the reviewer thinks that they should consider the scale of this experiment. Even a little bit of temperature change in this experiment can have a very significant change in the results. So these are some of the missing points. First, they didn't confirm what source of the sound was. Perhaps it was actually from the coil, but they didn't know. And how irrelevant noise could be prevented. And also the harmonics of the ferrite and what circumstances could the sound be significant enough for analyzing. How the temperature will affect the whole setup. Namely, the magnetic moment will be disturbed. And how heat produced in this system could change the whole experiment results. And also, they lack intuitive explanation of why ferrite is so essential. What is the essential point of using a ferrite? If we use a magnet, will there still be a similar effect? And also, the voltage and current boundaries. Are there a boundary for the current for the sound to be produced? And also, the relationship between the strength of the magnetic field isn't really changed. And how would the natural frequency of the ferrite change the experiment results, and also some qualitative theory and comparison between their theory and their data. Thank you.
Okay, thank you. So now is the time for reporter to make a concluding remark. 2 minutes.
Okay, so thank you, reviewer and opponent. For our research, the participants said that some frequencies the rod makes a sound. So we choose to focus on the frequency of the rod purely for this research. And the maximum sound per human ear is about 20 kilohertz. And the maximum frequency we measured was 70 kilohertz. So I believe most of the sound of the ferrite rod was measured and verified. For the coil, I think the magnetic field in the coil is mostly uniform because it is a solid rod. We also try to keep the rod in the center and parallel, so the field going through the rod is uniform. regarding the intuitive explanation, I think the environment is sound because when a signal generator drives the coil makes a magnetic field, and the field will cause the rod to vibrate. When the vibration matches with the natural frequency of the rod, by definition of resonance, a sound can be heard. And regarding the input and output frequency, I believe they're closely related because when we view the rod on the microscopic level, when the field changes, the domains will sense the force, so it will rotate pretty much instantly. And I think that causes the input and output frequency to be similar. Yeah.
Okay, thank you. So now we proceed to the question of the jury. So I would like to ask three presenters to stand on the stage, please, to the presenter. So any question from the jury?
Okay, a question for the reporter. You are saying that you see the resonance of the ferrite, but you are sweeping the frequency. Have you adjusted the frequency exactly to the resonance? Have you ever checked whether you do the resonance?
Yes, we adjusted and we do hear a small humming noise.
Do you have the data?
Data, the FFT.
This is sweeping.
Yeah, sweeping.
You don't have to adjust it.
We did not measure the sound, but we can verify.
Okay, then what the Young's modulus and shear modulus have you done?
You mean,
The Young's modulus and the shear modulus.
you mean how they affect the sound?
No, the value
Is
is
the value we have, is that the correct number?
We determined this experimentally.
Yeah, have you checked with the property of the material?
We checked with online references, and this seems to be higher, but it may be because the ferrite is made of different material. Like it has different material.
What's the error percentage?
I think each ferrite on the different references, they have different Young's moduluses. So that's why we try to measure it experimentally by ourselves.
So you don't have the error.
Any questions?
Technical problem. Very common. From the report, in your measurements of the shear waves, what did you do to the sample to ensure that it's a shear wave?
We did, because we only attached tape only longitudinal waves.
Tape to wave.
We take the whole rod basically. The rod.
You know the shear wave, the shape will change, right?
Yeah.
So you just surrounding the current sample, the ends are free. Is that right?
Yes.
But that will cause longitudinal wave.
Yeah. That's what we measured from our experiment.
So why aren't these modes common? Because the poles are all longitudinal. The Young's modulus, you only consider the longitudinal force, but the shear waves, of course, is in the same direction as fluid.
Yes.
So the equation of motion should involve both moduli. Is that correct?
Yes, we consider both modulus.
But in measuring it, shouldn't they be mixed?
The vibration, one is in vertical, the other is in horizontal. So I think when we prevent the vertical vibration, we already dampen the transverse wave. Because transverse is mainly in the vertical direction. And
So I think you consider them separately, not there is no conflict between them, right? So any questions Okay, since there's no other questions, so we forward to scoring. You can, if you want, you can ask, please.
I have one question for the reporter. What is the rate of your, because you do the sweep frequency from the 100 Hz to 30 kHz, and what is the separate rate of your microphone? Because
thank you.
because you need to double the frequency for the FFPs.
Yeah, 7 minutes 40 kilohertz.
40, okay, and for the opponent. If the temperature of the rock, the range of the temperature is about maybe 10 degrees, how would you expect to see the change of the magnetation, and that would lead to the change of the frequency of the sound?
Because as we know that
Please give number.
Every temperature has a different number.
If the change of the temperature is only about 10 degrees.
10 degrees.
Yes.
Yeah. As we know that the permeability was not changed at the low temperature, but in the high temperature, that over the curing temperature.
The room temperature and the room temperature. If your rod changes from 25 degrees to 35 degrees.
Yeah.
Yes.
I think that this will not be significant.
Okay. I think that's it. So, okay, since the question time, so we proceed to the scoring part. Okay, since all the jurors finished their work, so we start the score for the reporter. 6, 8, 7, 7, 7, 7, 6, 8, 6, 7, and 7. So then the score for the opponent. 6, 6, 7, 7, 8, 8, 7, 8, 8, 6, 5. Finally, the score for the reviewer. Please. 6, 7, 7, 7, 8, 7, 8, 7, 9, 6, 7. Okay, so for the reporter, we got the 3, 6, 6, 7, and 2, 8. So there are no obligation to give comments, but we welcome for one comment. No? Okay, please.
Say something. I think you spend too much time on explaining velocity equation. That's really, you just call the formula. That would be enough.
Okay, then for the opponent, we got one lowest mark 5. So please give some comment, and please give comment starting from your partial grade. So they will be one clear. If you just read it is okay.
0.7, 1.7, 1.8. That's the partial grade from me. And the main point that I didn't give a high score is that if we are going to spend too much time on the points that it's not so relevant, like this phase change, and you ask a couple of questions that's what should I say, like the definition of some frequency, where is it real domain or a simulation? I think these are not so relevant.
Okay. For the rest of the score, we got 3.6, 3.7, and 4.8. So are there any comments from the 8? Okay, please. Okay, for the reviewer, we got 2.6 and many 7, 2.8, and 1.9. So, any comments from the 9 even? Yeah, please. And also, please start from the partial grade you did.
Okay. For the reviewer, I give the partial points. I give you 1 point when you review the report. I give you 2 points when you review the opponent. 1.5 points when you discuss the analysis which was made by the reporter. And I give you another extra point because you point out many points. That's why I give the highest scores.
Okay, thank you. So, any further comments? Yeah, please.
For the reviewer, it's good to show how there are lots of missing points. But then I would suggest that you should better emphasize on certain important missing points. Then leave the rest on the screen, not read everything. Because when you read everything, that's when you think the mom is done. Okay, that's basically.
Okay, thank you. We finish this round and take 10 minutes break. Okay, thank you. Okay, I think it's almost time, so we wait for the juror to get back to the seat. Okay, for the third round, we have Cecilia as the reporter, the Miracle as opponent, and the All-Nighter as reviewer. The problem to be presented will be Sweet Mirage, and so I think we start from the time for preparation of the reporter. Clock, please start. Thank you. And reporter, when you are ready, you can call me. start your presentation. Time is 12 minutes, please.
Thank you. Honorable jury and all competitors, I'm the reporter from Team Excelsior, and today I'm going to present the problem number 5, the mirage. So the problem statement mentioned that Fata Morgana is the name given to a particular form mirage. A similar effect can be produced by shining a laser to a fluid with a refractive index gradient and investigate the phenomenon. In my opinion, I think the main problem should be what is Fata Morgana, why Fata Morgana happens, and how the position of the object and the observer, and also the changing gradients will affect the phenomenon. So why mirage will happen? The mirage will happen because there is a temperature-dependent gradient of refractive index in the atmosphere, with colder air with larger refractive index at the bottom and warmer air with smaller refractive index at the upper part of the atmosphere. And in this time, it will create superior mirage, which will cause the light to bend downward as the light passes through the refractive index difference. And as our eyes tend to trace back at straight lines, we will see images that is not at its original position, which we call it mirage. And why is Fata Morgana different from other kinds of mirage? Because Fata Morgana is a superior mirage is required for 3 and more uplifted images, which means that multiple images will be considered in this phenomenon. And why multiple images will happen is because there's a large gradient sandwich between 2 smaller gradients, and it will cause this part with strong refraction and this part with weaker refraction to cluster into each other. And then in our eyes we will think we see 2 different kinds of images. So we will see multiple images in our experiment. So the non-monotonic gradient is quite required. This is the observation of Fata Morgana in our lab. Instead of using the temperature-dependent refractive index gradient, we carefully control the concentration profile in our experiment to create refractive index gradient. And in this chart, you can see that there are 3 pictures of Fata Morgana of a 5-image mirage in our experiment. And we use both model because it can help us to clarify if the image is inverted. And laser pointer and laser light respectively can help us to know whether the point is focused. Because if the light is focused, which means that we can see more sharp image. And also, this drift file shows the up and shot at different heights, and so that means that the vertical height of the observer can also affect the phenomenon largely. This is my outline. First, I will talk about the working principle of Fata Morgana. Then I will talk about our experimental setup, and talk about the result, and discuss about 2 main parameters, which is gradient, observer's position. And then I will conclude my report with the boundary condition to observe Fata Morgana. So first, in the theory part, in our experiment, we assume that our medium is uniform in horizontal plane, which means the refractive index is constant in z-axis, which is the horizontal axis, and it will be a complex function in y-axis, which is the height in our experiment. And also, by using Snell law, we can use the obtained theta angle, which is the incident angle, and using the obtained horizontal distance, which is delta c. And use Snell law to calculate the deviation angle, which is delta theta, and the displacement vertical, which is delta y. And by algebraic the arrangement of formula, we can see that with increasing refractive index gradient, we can enlarge the deviation angle. And with larger deviation angle, the distance to Fata Morgana will become shorter. And this can help us to use a tank, which is then 60 centimeters in our experiment to observe Fata Morgana, because the sugar solution gradient is much bigger than the gradient in air. And as we have to imply which kind of gradient we have to use in our experiment, we use ray tracing simulation to compare the difference between different kind of gradients. The first case is the linear refractive index profile, which is the negative constant gradient. And you can see that we will only observe one uplifted image with no deformation, so it will not be Fata Morgana. And then with exponential decay index profile, which is the gradually decreasing gradient, you will observe one smaller image, which is uplifted, but it's only one image, and so it is not Fata Morgana either. And we think that we can use arrow function index profile to observe Fata Morgana, because it's a monotonic gradient with small, large, small gradients. This will affect because when the lines are passing through large refractive index weekly. And when they cluster, we can observe phantom in this part. And why we are using arrow function is because that in fixed second law, it seems that arrow function is the typical kind of diffusion between concentration. And as we use concentration profile to create a refractive index gradient, we think that we can use arrow function as a refractive index profile. And we use scale length to describe the width of the diffusion zone. This is our experimental setup. As you can see that I stated we use water, the diffusion between single solution to create a refractive index gradient. And also we use laser beam light to put light trajectories through the tank. And that we can take side shots to record the result with the camera. And also we can take a side shot at the end of the observer plane with the camera with called end shots. It's because that when we replace the both model to the laser pen, it can help us to clarify if the both images is inverted or not. And also it can help us to clarify how the image looks like. So first I'm going to talk about my first parameter, which is the refractive index gradient. So how do we measure the refractive index gradient in our experiment? I think there's one efficient way that we can measure the refractive index gradient by using the displacement horizontally of the scatter of the laser beam. So by starting the laser beam vertically into the tank, we can see there the scatter of the laser beam will pass through different kind of refractive it passes through the tank. And as we take side shots, we can see this displacement and use this to calculate to derive the refractive index using Snell law. And then, as we measure the refractive index profile, the temporary evolution of the refractive index profile with time is indicated. So in this chart, you can see that the profile is flattened time, which means that the scale length is bigger. And with bigger scale length means that the width of the diffusion zone is bigger. The refractive index gradient will become smaller with time. And this is an example taken about how of laser beam light trajectory in our experiment. So we use a diffraction gradient length to create multiple beam light multiple beam light trajectories, because this can help us to clarify where is the interaction point of our experiment. If the interaction point is important, it shows that we can observe phantom organa at the intersection point, which is the all light clusters into each other, and we can see multiple images. And also we take side shots. So this is the experimental result about this experiment. The ray trajectory under different refractive index gradient is investigated. As you can see, as the flattened profile of refractive index was flattened, the scale length is bigger, and the intersection point, which is like this part, and this part, is moving forward, moving towards the end of the tank, which means that the horizontal displacement, the horizontal distance is become bigger with the smaller gradient, and this result proved in our survey. And also we take end shots and use phantom organa under different refractive index gradients. This is the observation we take at the end shots. As you can see, when time passes, the gradient becomes smaller. We can observe more images at the bottom of the tank, which help us to know that the intersection points also moves towards the observer's plane. So these two experiment results are fitted. And also this is fit with our theory. And this is an electricity simulation that we have to use to clarify if our experimental result is accurate. You can see that the electricity simulation is very fit with our experiment, which is the index focal. And also the position of the light, the overlap is around this area, and this fits with our experimental result that we observed in the observing plane. That I will talk about later in observer position and the second parameters. And also we use simulated position of ray arriving at the observation plane to see where we can see phantom organa at the distance between us. So the circle part is the place that I think we can observe phantom organa. As you can see that it's become more concentrated as time passes, because the intersection point is moving towards the end plane of the tank. So it means that more light from different angles clusters, and we can observe phantom organa more easily. But as you can see that the overlap distribution we will with time. So I think the distribution position will also be important. So I'm going to talk about what that means, which is the second parameter, the observer's position. So I take end-shot image recorded at various heights. As you can see that the vertical height will affect the formation of the mirage dramatically. As you can see that we can see more the mirages of Fata Morgana at this part, which is just below the boundary and below the diffusion zone in our experiment. And also using the geometric factors, using geometric function, we can trace back as straight lines by using the arriving angles and the position of light, and to create a simulation of how we can observe mirage in different kind of different position. And as you can see that the position is at this place. So in this part we can observe Fata Morgana, and this also fits with our experimental results. So in the conclusion part of the optimal condition to observe Fata Morgana. First one is the best observation distance to observe Fata Morgana for different scale lengths for different diffusion zone. As you can see that in this graph I show the best observing distance and scale length, and it's almost linearly proportional. So as you know that the scale length will be inversely proportional with the refractive index gradient, and the observer is proportional with the length. We can know that the observer distance is inversely proportional with the gradient, which is fixed with our theory, and this is the result of our theory too. And also the second is the best time to observe Fata Morgana. As you can see, it will change dramatically of the formation when we move observation's height. And we can observe Fata Morgana here, which is just below the region of the boundary and the diffusion zone. And also, we use simulation to show where we can observe Fata Morgana. And in this chart, we show that if we state the position and wait for diffusion to take place, we can observe Fata Morgana at any position. And also, it is possible for us to see other two kinds of mirages. So finally, just for reminding, standing at the proper distance and height, and let the diffusion take place and set the stage for Fata Morgana. And then we can observe Fata Morgana, which is a phenomenon. Thank you.
Okay, now following is the question of the opponent to the reporter for 2 minutes. Reporter, please be ready to answer.
Hello, I'm the opponent of Tigger, and here are some questions for you. So first of all, how does the light goes in your glass? How does the light, is there an angle, a constant angle, or how is the trajectory of your light?
Do you mean the incident angle?
Yes, yes.
Yeah, we use different incident angles, and they are fixed.
Okay. And next, how do you measure the index of refraction?
Sorry, please do page with refractive index. Yes. And this we use the displacement of the scatter of the light beam that shot vertically.
So you use the Snell's law to predict the refraction index of refraction.
I didn't predict. I calculated.
Okay, thank you. Next, why do you use a boat as the object? Does the boat float in the fluid?
I'm sorry?
You said you use a boat as the object, right?
Yes.
So the boat float on the fluid or?
No, it's outside. It will replace the position of the laser beam.
Oh, okay. And next, can you turn to page 60? 60? Yes, and compare it with page 20.
Compare with page 20.
Yes, I believe that did it change the frequency of your light because some colors are like green, blue, and red.
Understand. These are in this area is the sugar solution area, and this area is the water. So the color of sugar solution will be important.
So you said that the color difference is because the concentration of the water.
Yes.
Okay, thank you. And lastly, still on page 20, and how do you change your height?
How do I change my height? I use stacks of to power up, and each stack is 1 centimeter.
Okay, so the height change is constant.
Yes, it's constant.
Okay, thank you.
Thank you.
Okay, now is the time for opponent to prepare for 3 minutes. Okay, I think it's now time for the opponent to take floor for maximum 4 minutes. So please start.
Okay, good morning, ladies and gentlemen. I'm the opponent from徐有庠, and today I'm going to oppose cover number 5, Steve Rod. From the opponent's perspective, we give the ideal structure of investigation. First, we need to define Fata Morgana, which includes distorted and many images, where here the reporter gives a good definition of Fata Morgana. And next, we will analyze the light path and information of the image. Next, we will observe and predict the image properties. And lastly, we will have a new understanding of, and here we have predicted if there is or no merit by the RI profile. First of all, I would like to thank the reporter for hard work on her reporting, but there are some pros and cons that I have to point out. First and foremost, here the reporter gives a clear definition of Fata Morgana, and actually the reporter knows that she can use a Snell's law to simulate the trajectory. Next, the reporter controls the RI gradient, which is the reflection of the index gradient, really precise. And next, the reporter changes many parameters, and lastly, the reporter gives a clear oral presentation. And next, here are the cons. First, the reporter uses only Snell's law, which, in my perspective, I think it is insufficient. Next, the reporter gives the clear relationship between simulation with observed phenomenon, since she only gives the trajectory from the laser and did not give the position of observation. And next, there are many graphs not going to explain, or I'm actually including the maps, the lines that are crossed together, and she didn't point out the important point. And next, she didn't provide a perspective of photos, and it is hard for us to tell that whether when one light goes in, where is the observing position. And lastly, I think the reporter didn't have a new understanding and a conclusive result of the phenomenon. So these are the points to be discussed. First, we'll discuss the phenomenon, which is the mirages. First, we'll discuss where there is or no mirage, including the light trajectory shape and how does the reporter observe the position of the image and the shape size, distortion, and the critical property of the gradient profile that makes Fata Morgana, and next the observing angle and height. And lastly, that, as I said, the conclusive understanding of the reporter. And next, modeling of light uses Snell law, and I believe that it is only in limited cases that the Snell laws can be used. And I think that you need to consider the properties of wave in light using Huygens principle. And you should change the beam width and intensity, since I think that will also affect the phenomenon. Next is experiment detail. I think that the validation is deltable with the measurement of the gradient. And next, I think the reflection index and concentration are also need to be concerned. Lastly, the parameters. I think the temperature will change the diffusion of the concentration of the water, and next different frequencies of light. And now I'm going to begin my discussion with the reporter, please. So first of all, can you explain that what conditions of the...
Wait a minute! Sorry, the clock is not changing.
Okay, thank you.
So first of all, can you explain again in what conditions of the trajectory shape of the light will cause Fata Morgana phenomenon?
It depends on if there are interlays of different various degrees.
I'm sorry, can you give an intuitive diagram on the white, please?
Okay, so if there is the shape, we cannot see we can observe Fata Morgana with just one trajectory. If there are a lot of trajectories that cluster into each other by the same object, and at this part we can see multiple images, and we think it will be called as a mirage.
And can you explain why will there be some distortion of the shape and something like the image will be upside down?
Okay, so can you come to the page with the definition of Fata Morgana? Thank you. Okay, so in this picture you can see that it is an inverted image here. It's because that when light passes through here, the large gradient, it will maybe there will cause a crossover of the upside the light come from upside and the downside and the upside. And when they cluster, we will think that it comes from this side, and we will see the upside down images.
Okay, so you mean that the most important point is that all the lights are crossed?
Yes.
Okay, thank you. And next, what do you think that is the critical property of the gradient profile? As you said that there is a error function, you assume.
I think that it should be non-monotonic, because if it's monotonic, there will not be the gradient differences in the middle and the up, down, and stuff like that. So it will not cause different kind of refraction.
Okay, so can you explain that? You say that the function of the gradient relative to the height is a error function. Why is that?
Because we use concentration profile to create refracted index, and in Fick's second law is mentioned that the concentration profile diffusion will make the concentration profile looks like the arrow function that look like this.
And can you elaborate the significance of it as the error function, as you say that the...
I'm sorry, maybe you can listen to this one.
You say that the function will look like this, right?
Yes.
So you said it's an error function.
Yes.
But as we have considered it is a function such like x equals y to the third power, do you think that this differs from the error function and impact the significance of these beta Morgana?
Well, I think if there is a non-monotonic gradient, it can produce Fata Morgana, and no matter if it's error function or not.
Okay, so then the error function is just an intuitive assumption that you think that the diamond is an error function. Okay, thank you. Next, can you after the report, can you predict the images by beta Morgana when you see a function of the index of refraction? If there's something like this or like this, can you predict what will happen when something that differs from an error function? What will happen?
Do you mean like this is the refracted index profile?
Yes, it is.
Yes. And so for like this kind of index profile, I want to ask if this axis or is y-axis, which is the height axis.
Yes.
Okay, so in this part, the refracted index is small at this part and high at this part. So it is not Fata Morgana because it will be an inferior mirage, and Fata Morgana is a superior mirage.
Okay, thank you. And actually, you only use the Snell's law to simulate the trajectory, right? But you only use the Snell's law to simulate the trajectory. Snell's law.
Snell's law, yeah.
Yes. But have you ever considered that the wave properties of a light? Because here you can see that if this is your experimental setup, and here is the index of refraction.
Yes.
If you use the Snell's law, you can see that when the light goes perpendicular to here, it will go straight, right? Because
yes, it will go straight.
Because you assume that the index is only y-dependent, right?
Yes, yes. Y-dependent.
Okay, sorry. Y-dependent. But if you consider that the width of the light, because in Huygens principle, it is considered that one light is a plane. So if there is a plane goes here, it will process different index, and here by Huygens principle there is a larger circle here and a small circle here, and this will causes a different simulation to your simulation.
Yeah, I understand, but if you are mentioning about the width of the laser beam, are you talking about the width of the laser beam, like the beam light is like this and it's kind of width?
Yes.
Yes, so in this picture, which is not observation, you can see that the light will also have deformation. So we didn't consider it because if you think that it had width, you can just simply have two light waves related.
Your assumption that is the index of reference, the index of the refraction is continuous, right?
Yes.
So there must be, when a light goes in by Huygens principle, there must be it must have a different trajectory as your assumption using Snell's law, right? How do you calculate for this two different phenomena?
No, first this is I think this deviation with the width is negligible in our experiment because the light is very small. And also, if you are going to mention about it, I think the laser pointer there, the image also deforms, so it can be shown that it is
with our experimental results can also show how the width will affect.
The point is that because your width is so small that you can consider it as a continuous, so the light will definitely crosses other index of refraction that makes the trajectory bend.
You already mean that when the light is incident in 0 degree?
Yes. I know that because by previous principle it will bend.
Sorry, I disagree because in my experimental assumption, I assume the refractive index is constant in z-axis, which means that it will not pass through different refractive index when it is in.
Yes, because you only consider the geometric factor of the light, which is a single line. But if you consider as a plane wave, it will bend. Okay, so next question is your experiment detail. You said that you can read how you measure the gradient.
I measure the gradient, yes.
How do you measure the gradient?
Actually, I measure the displacement of the scatter of the laser beam here, and because that if the laser beam, the tank will look like this, and if we insert a laser beam, it will passes and with our camera recorders, so it will passes through the diffraction.
Yes, as I said that you first see the trajectory and calculate the Snell's law, right? But as I said, your Snell's law may not be efficient. It may not be sufficient enough. So suggestion is you can put a pin in there and suck the liquid out and test the concentration and know the theoretical refraction.
Well, I don't agree because I think that way is inefficient, and also it will change the refractive index in the horizontal plane. Because if you suck out the liquid here, parts will go down and affect the refractive index.
Okay, and next, in the same page, you can see that in this way you only draw one point. How do you assume that here and here is a straight line? It may be like this or like other.
So actually we measure all the points here and we have the points on
draw 1 point?
Because I think this can make the slide less nasty, but I do have measured all the points.
Okay, thank you. And finally, to our parameters. First, do you think that the temperature will have a significant influence on the diffusion of the concentration?
Well, in our experiments, we will control the temperature, and also I think the temperature will change diffusion. It's correct, but the phenomenon isn't about diffusion. It's about the refractive index. So as long as I can measure the refractive index, the change of diffusion is okay.
So can you say that in every experiment the temperature is a constant?
It's a constant because we put it in our lab and the temperature is a constant.
Okay, so finally to my last question. We derived by the equation that the frequency of the index of refraction changes as the frequency of the light changes. Yes, do you think that will affect your phenomenon? If you use a purple light, it may have a greater index of refraction, and if you use a red light, it may have a smaller index of
Well, I think that it will change very slightly, so it's negligible, and also because we observe objects, and objects will
but I think that is not very slightly. You know that when it goes through a prism, and the light will separate this, and I believe that is not very small.
Yeah, but because we only have to observe one phenomenon happens and then the manufacturer, and as we observe the object as a mirage, it will have.
Yes, but I do think that in different colors, and such that in different frequencies, it will different maybe with purple color, and the phenomenon will happen, and with red color.
The reporter thinks that it will only cause slightly difference, and the trend will be the same in our experiment.
Okay, thank you.
Thank you.
That's it.
Okay, thank you. So now it's 1 minute time for opponent to summarize the discussion. Please.
Okay, so first of all, we discussed the formation of the Fata Morgana, and the reporter did a simple and clear explanation of the formation of the Fata Morgana. And next, I asked the critical property of the gradient, and said that the error function is only an assumption that is intuitive to the diagram, but I think that it may not be an error function, and as you can see there are full ways to show that it's that diagram. And next we have discussion on the theory of the cells and biggest principle. The opponent still believes that the biggest principle is significant to the problem instead of the Snell's law. And actually have the discussion on the experience measurements, and that's we have the discussion of the parameters which she didn't consider.
Okay, thank you. So, following up is the question of the reviewer to reporter and opponent. Please.
Okay, reporter, do you think the action of pouring the sugar solution into the tank disturbs the existing solution? Yes or no?
Yes, it will affect.
Okay, so did you try to reduce the disturbance of the solution?
Yes.
Okay.
Yes, I believe.
Also, do you account for the angle of refraction of your container?
Of my container, I don't think that will affect the phenomenon. Because all the lights will reflect at the same, and the displacement will be the same. So it will not affect the whole phenomenon.
Okay, opponent, do you think the reporter's current method of correcting for the refraction of the laser through the tank is accurate and reliable?
I'm sorry, do you mean that the measurements of the reporter? The measurements of the concentration? No, I believe that it's not reliable. That they vary the concentration in every experiment.
Okay. What do you think will happen if the reporter uses an electrolyte instead of sugar?
Electrolyte. I believe that the sugar is a sufficient fluid to produce the phenomenon, and I think that is.
Thank you. The reporter, what do you think will happen if? Why do you think that the light spreads out at the end of its trajectory?
So sorry.
Why do you think the light spreads out at the end of its trajectory?
Because there is the place of the light beam, but it will only affect the zone.
Okay, what does the opponent think?
I believe that when the light spread out, it means that the concentration of the liquid in the end is not a constant, and it is somewhat massive.
Okay, thank you. Reporter, did you consider changing the wavelength of the laser because shorter wavelengths have a higher next reaction?
Sorry, changing the what?
Wavelength.
Wavelength?
Wavelength of the light of the laser.
Changing the different kind of laser?
Yeah.
I don't think that will affect the trend in our experiment.
Okay,
I believe that is a very important point, as you can see in this prism experiment, that the index of refraction changes very much, and that causes, when you use a red or purple, it causes a exactly different phenomenon.
Thank you. Reporter, do you believe Snell's law still applies in this scenario, even though there are infinitely many index of refractions? Because the gradient
Yes, it is reliable. Snell's law is relevant in our experiment.
Okay. Also, what are the limitations of a theoretical model?
Well, it's assumed that, I think the theoretical limitation is that it needs to be an incident angle, and we have to use we have to have an incident angle and obtain horizontal distance to do our simulation.
Okay, thank you. Lastly, what do you think are the key differences between... Never mind, it's okay.
Okay, thank you. So now, reviewer, you have 2 minutes to prepare your presentation. Okay, time is up. So, you will please take the floor for 4 minutes.
Okay. Hello, I'm Richard from Team All-Nighters, and I will be reviewing number 3, Super Mirage. So, what we believe the main focuses of this problem statement is one, what is the Fata Morgana and how is it created? 2, how can we replicate Fata Morgana and with a refractive index gradient? And what are the relevant parameters that affect the path of the laser? Okay, so the reporter's performance. First, they went over the phenomenon and they talked about what the Fata Morgana was, and they compared the superior and inferior images. Then they went into their theory, and which included Snell's law, and they used the gradient simulation to show the trajectory of the laser. And they also used 6-second law and a non-monotonic gradient in their experiment as well as the theory. Then they used in their experiment they layered different concentrated solutions and let them diffuse. And then they also tested the observer position from outside the container, as well as the object position, and they changed the gradient in their experiments. Some pros of the reporter are that they had a very clear speech, they had a vivid presentation, they had a very nice experimental setup, and a lot of graphs. And they considered many parameters, and they had great time control. Some things they can improve on is that their phenomena explanation can sometimes be more concise. They have some lack of quantitative predictions, and they have some confusing graphs, and they could use the refractometer. So the summary of the opponent's performance is that they discussed the mirages, the modeling of the light, and some experimental details of the reporter. Some pros are that they mentioned that the wave nature of the light height is principal, and they considered some new parameters and topics in their discussion. However, they did not focus enough on the experimental errors of the reporter's experiment and how to improve those experiments. So the first point of discussion was, what is Fata Morgana? And the reporter said that there are multiple light rays instead of just one, and you can see multiple images. And the reviewers, as a reviewer, I agree, for one full image to be seen, you need multiple light rays in order to see that image. The next discussion point is that the opponent used Snell's law to simulate the trajectory and the wave proportions to the spreading out of light. The reporter did not consider this because she thought that it was negligible. I strongly encourage the reporter to consider this and verify that this in fact is negligible for the laser, which has a width. And you can do this experimentally. The third point is that the opponent asked, how did you measure the gradient? And the reporter said they measured the displacement of the scattered laser beam and mathematically calculate the gradient. I believe that you should use a refractometer to verify that the exact nature of the refractive index gradient is what you think it is. And we agree with the opponent that this is important to the experiment because at each height there should be the same gradient. The last point of discussion is the other parameters significance, and the reporter said they control temperature and it's not really relevant. I agree with the opponent that the frequency is very significant, and the reporter should measure the temperature with a thermometer to verify it, and we agree with the opponent that these variables matter. So some points missed is that the reporter could use a quantitative prediction, for example, an Euler-Lagrangian, which optimizes the path of least time, which matches up with the Fermat mass principle very well because the light takes the path of least time. The reporter had a Thank you.
Okay, thank you. Now is the time for reporter to make a concluding remark. 2 minutes, please.
So I'm going to start my conclusion of my result. So what is Fata Morgana? Superior mirage is more than 3 images. And when Fata Morgana happens, there is a normal and fully refracted index gradient cause the difference of refraction and creates multiple images. And then about the conclusion part of my parameters, first gradient will vary with diffusing time and is inversely proportional to the horizontal distance of Fata Morgana. And then this position will change the phenomenon by as same as moving the position of the large refractive index gradient sandwiched between two smaller gradients. And also, the observer's position will affect because it will affect the shape and the number of the image. And also, we use M shots to get the the observing image at different heights and use simulation to help analyze the data, which means our experiment is quantitatively predictive. And also, the best to observe, the phenomenon is best to observe under and near to the large gradient. And these are our remarks. So first we use scatter incidence angles in our experiment, and they are all fixed. And I use this to observe the interest points in our light trajectory. And also we calculated the refractive index by using horizontal displacements of a vertical incidence laser beam. And we think that is efficient and also is accurate. And then we check the parameters constantly, and also the theory can fully explain the phenomenon, since we can use simulation to simulate all the situations in our phenomenon. So the phenomenon becomes predictable. And also, the condition of phenomenon appears to depend on different parameters, and for example, the gradient and observer's position. And I think the frequency of light will not affect much, since it will follow all trends because they are all rays. And also, we think that the color of laser will not affect much, and we made the results quantitative by proving the linear proportional between scale length and observing distance and build simulation. Thank you.
Okay, thank you. Now it's time for jury to ask questions. So all three presenters, please stand up to the stage. So, questions.
Okay, I have a question for the reporter. Could you tell me in the nature what condition you see the phenomenon?
Well, it follows it is a warm day, and there is a tide flows into a strait and bring the cold water into the surface of the earth, and it will create a refractive index gradient. So it happens in high latitude ocean area in the Earth.
Okay, a short question for the opponent. Why do you think the Huygens principle is important?
Because with the Huygens principle, we can derive a completely different phenomenon with the Snell's law. So I think that there's a contradiction, and we can investigate on the Huygens principle.
What difference?
As you can see that, as I said, that when the Snell's law, when the light is perpendicular to the plane, it will go straight through the water. But if you consider the Huygens principle, it will still bend. So then it's about going in a straight line.
So any further questions?
In measuring the index of refraction, you mentioned you use displacement method, and you say this one.
Yes.
So you shoot it from top.
Yes.
And then you analyze the displacement at the various depth.
I'm sorry?
You're measuring the profile of the index of refraction.
Yes.
Right? Now you assume that in order to determine the index of refraction at certain depths, you should look the displacement of the light at that depth, right?
I use the whole line too. I measure
the whole line is okay, but you measure the displacement at certain depths, right?
Yes. Thank you.
And I forgot which one mentioned about using the reflectometer. Is it so? What kind of reflectometer you have in mind? And do you know the principle of that reflectometer?
All I know is that the refractometer can help us measure the concentration of the gradient.
So you don't know the principle, basic principle of the reflectometer?
Sorry, no.
So do you, unlike the opponent, do you know any kind of reflectometer?
Yes, I believe that there is some. There's something that you can put the liquid on it and finally you will know the.
No, I mean you know the principle, working principle.
I don't know the principle.
And how about the opponent?
Well, I think it uses the deviation angle.
Yeah. Okay.
Yes, thank you.
So any further question? Please.
Question for viewer. Like this slide, you mentioned about the information about not using the, for example, order, graphing, or the purpose is unusable. Can you tell me what the difference from the Snell's law?
Snell's law only is more useful in a situation where there's only one boundary condition, and like you have a laser coming through and it'll only bend once. But since in this situation we're saying that it's a refractive index gradient, right? So the gradient is constantly changing, and I think optimizing this path of the light to take the least amount of time will help us determine this better.
I think Snell can also help us to predict the continuous angle, continuous ends of the airflow, the light rays. Because if we deviated the refractive index profile into different stage, and we can use Snell law, because that like in my theory, I said that we can have like this part. If we deviated the index profile into different stage, and we can into very little stage, and it can become continuous. Thank you.
Okay, I think the question time is almost up. So if there are no further urgent questions, we move to scoring. Okay, since all jurors are ready, so now the score for the reporter, please. 8, 8, 9, 9, 8, 9, 8, 9, 9, 9, 7. And score for the opponent. 6, 8, 6, 6, 7, 7, 7, 7, 8, 6, 7.
Thank you.
Then the score for the reviewer. 6, 7, 6, 6, 7, 7, 6, 7, 6, 6, 7. Okay, for the comments, we get a lot for the reporter, 1-7 for the reporter. So I think we need some comments from the 9th and definitely the comment from the 7th. So who will give the comment first? Okay, 7 first.
Okay, I think the the reason I did not give an 8 or a 9 is that I think the discussion is a little bit, how to say, the discussion between you and the opponent, I think it's more like, I don't know how to express it very well. I mean, it's not helping me to understand better. That's my point.
Okay, technical, maybe, right? Okay, so I think we need some comments from the nines. So, can you give some comments?
I think the reporter is doing a great job in the experiment and the theoretical explanation. And the Stanley's law basically covered different math principles. This is just for information for the viewer. And the only reason I did not give you a 10 is you good way to explain everything from intuitive thing. That this is great. But you did not really connect numerically or quantitatively from your theory to your experiment. This is the little bit distinction.
Okay, thank you.
Okay, for the opponent, we have 4, 6, 2, 8, and the others are 7. So I think for the 6, we need some comments. So any comments from the 6?
Okay, I think I deduct points from your answer because you keep insisting Huygens principle and Snell's laws are incompatible. Whereas, as Shi just pointed out, Snell's law, of course, applies in medium to this continuous or discrete change of index of refraction. It's okay. I think wave optics is only important when you encounter restrictions or like a screen or a hole with certain dimension. And I think that we make some mistakes of agreeing with the opponents. For this point, the reporter is correct. When the laser light shoots horizontally along certain depths of the solution, the lights will bend because the light has width. Light it's not just a thin line, it has a width. So the index of refraction, the change, the gradient of the index of refraction will make the lights at the top go faster, where the bottom will be lower, so it will bend. And this can be accounted for with Snell's law. It's okay, because the situation you're considering is that on the other side, the index of refraction doesn't change. In that case, of course, the incident rate will keep going straight. But as long as there's an index of refraction in the solution, the light will bend. Okay?
Understood.
Okay, so any further comments? Yeah, please.
I'll give him 8 points for the opponent because I think he really listened to the reporter and point out many good questions, and especially the color of the picture problem, and then he tried to give you all relevant points and provide new crucial points to discuss with the reporter. So that's why I give him higher scores.
Okay, so finally for the reviewer, the grades are quite even. We got 6, 6, 5-7, so they are quite even. So I think give some comments is nice, so anyone want to give comments? It's not an obligation, but
I asked a question about the reflective spectrometer, which is used by the reviewer. I guess you should understand what you ask. Because what the reporter is doing is exactly what the reflectometer is doing. So that is why I would say that you should think about when you ask a question, you better have something in your mind that you can say something about what you mentioned.
Okay, I think I have some comments about this question. Actually, for the reporter's method of measuring the refraction index, it's equivalent to shoot the laser horizontally from the short side. Actually, it's the same. I don't know if you ever drawing any light path about the scattered light. If you drawing that, you will find it's actually the same. So I would say the better way to measure the diffraction index along the z-axis, it should be that you make the wall of your container, one of the side of the wall become a prism with a very small angle. Then you can make that wall becomes kind of a spectrometer, which one we use to measure the sugar concentration. Okay. So in that case, you can avoid the line path problem. Because in your situation, your scatter light still propagate inside the solution. So whenever you think it's going horizontal, it's still bending in any way.
Okay, thank you.
Okay, I think during your discussion, you try to convince the opponent and the reviewer about that part. You want to say that your method is better than shooting a laser horizontally. So, but I think actually they are the same. Okay.
Okay, thank you.
But anyway, so we finished our final physics fight, and I think we already know who will get the no. Okay. So anyway, I would like to close the physics fight of this morning and thanks all three teams bring us very brilliant solutions here and also hard-working jurors to jury physics fight. And thank you everybody. Thank you. OK， 我们接下来是午餐哦，那个后面有餐点，那各队的队员请就用你们的桌子吃饭。那前面3队，请你们尽快清空你们